right, thanks for the introduction. My name is Yudai Tanaka, and today I'm going to talk about Haptic Source-Effector, my latest work that I did in collaboration with Serfaty and my advisor Pedro Lopes at the University of Chicago. So this user here is immersed in virtual reality, and they feel the force feedback in their hand for being hit by a projectile. They can also feel this in their foot. So today's goal is to find out how he was able to feel all these sensations while he wears nothing on their hands and feet. So let's start with where we are today. I think we are in a very, very exciting time. And as you can see, like all these amazing haptic paper, and we have this session well attended. And there are so many great haptic devices that designed for creating sensations in the different parts of the body and designed to be attached to these target body part. So for instance, like haptic globes were designed to attach to the hand to render the sensation in the hand. Or haptic actuator on the arm or forearm to render force feedback to the arm. Same way, leg device create a sensation on the leg, or foot-worn devices to provide sensations even on their feet or sole. This approach of attaching devices to those locations, it's very intuitive, as in the users need to feel these stimuli in these skin regions where these devices are indeed attached, right? And those are the very endpoints of our nervous system that process haptic sensations. So we call this approach haptic end-effector, borrowing the term end-effector from robotics. But unfortunately, I believe this approach will not scale up to create sensations to the user's full body experience, because the user will be heavily instrumented to feel the haptic feelings in the different parts of the body, and these devices are all specialized and sometimes bulky. So today, I'm going to propose a completely new way to provide haptics that breaks away from this idea of endpoint actuation. But first, we need to walk through and understand how the end-effector works. So let's think about the user wearing a haptic device on their hand to feel the feedback in the hand. And the device applies the mechanical stimuli to the skin, and we want to know how does their body feel this sensation. Well, there are receptors on the skin that convert these vibrations or skin deformation or even force feedback to electrical signals that get transferred to the nerves inside the hand, relate to the spinal cord, and all the way to the brain. And it's only at that point when the signal finally has reached the brain that the person feels, oh, something happened in my hand. So if the brain is where all these sensory signals converge, what would happen if we bypass all these endpoints and only stimulate this point, the source? So that's the concept I'm proposing. Haptic Source-Effector. So let's get back to our original theme. Turned out, what this person wears is our brain stimulator device that leverages transcranial-magnetic-stimulation, TMS, which is a non-invasive brain stimulation technique established in neuroscience using an electromagnetic coil energized by a stimulator that is currently off the screen. So at this right moment, when the user should feel the recoil of shooting a projectile, the coil creates a magnetic field that stimulates the corresponding brain area, creating touch and force sensations in the hand. Now these sensations here are coming from the hand, but instead directly created at the brain. Now, when a user gets another projectile on the foot, the brain stimulator has now been moved to a different location, and this time create the sensation in their foot. As you've just seen, this single haptic device was able to switch between two areas, the hand and foot, and generate sensations although they are very, very far apart. And again, he is wearing nothing on his hand or feet. But our device can actually stimulate more than hands and feet. By robotically moving the stimulator across the head, it can provide force and touch feedback to jaw, arm, foot, leg, and hand. This is all based on the fact that this stimulated area of the brain in the sensorimotor cortex map to sensations from these body areas. So now, as you may be wondering, we actually formalize and investigate how many different sensations our current version of Source-Effector can create. We recruited 12 participants and we defined 9 points on each participant's right side of the sensorimotor cortex, which correspond to the left side of their body, and stimulated each point while modulating the stimulation intensity. What we found is that involuntary body movement, which is force feedback, occurred in these 6 regions, like jaw, forearm, hand, fingers, lower leg, and foot. We also observed the participants felt touch sensations without any movement in 2 locations, their hand and foot. So we observed the total of 8 different sensations within one side of the body, which doubles for the other side, so 16 sensations across the whole body. We also observed that these effects are quite evenly distributed across the 9 stimulation points on the brain. So this informed us we need our device to be able to control the coil position with at least the precision of the grid size, which is 8.5 millimeters. So now let's talk about our device. So this, on the left side, the blue one, is our stimulator, and the right side the user wears is our robotic device. And first of all, our device features 2 main motors. This rotational serve moves the coil left and right, and this one moves the coil front and backward. Importantly, we have another motor that adjusts the angle of the coil so that the coil is always attached and flush to the user's head. Altogether, our device can robustly move the coil with the required precision of 8.5 millimeters. Okay, so now we took that device and put it actually on user's head and let them experience our virtual reality application, which is our second user study. So our participants indeed experienced the walkthrough that you just saw in the beginning of this talk, feeling and shooting the projectile in the hand and feet, and even stomping on the box to collect more ammunition to shoot the projectile. And here comes their reaction. As you can see, people really enjoy the interactions, and we found that our new way of creating sensations directly from the brain was positively appreciated by the users, and they also mentioned it added to the realism of their experience despite the current form factor of the device. All right, so today I proposed Haptic Source-Effector, a new concept for creating haptic sensations by directly stimulating the brain. As opposed to conventional haptics and end-effectors, our approach allows us to reach many points across the body from a single device on the head without instrumenting users with many different devices and different locations. Haptic Source-Effector is also the latest and the most extremely version of my vision for intercepting the nervous system. For instance, in the last year's CHI, I presented creating touch sensations in the fingers and the palm by only having the device on the back of the hand. Or my CHI paper from CHI 22 presented our approach to move the user's head but without attaching any robotic instrumentation on the head. Or with magnetic muscle stimulation, which I presented in last year's wrist, you can stimulate the muscle without wearing anything on the muscle, but instead instrumenting the environment, not the user, with the stimulator. So naively, you might think that haptic source-effector rule all of these approaches out because the brain is indeed the source of the nervous system. But it turned out there's a deeper difference between stimulating nerves and stimulating the brain. For instance, if you think about the spatial resolution of these techniques, although we were able to stimulate and create more than 10 locations of the sensation in the hand by stimulating the back of the hand, as we attach the device further away from the hand and going to closer to the brain, the nerves are getting more bundled together, so it will be much more difficult to stimulate a smaller location from these points. So at the end of the day, eventually if we reach to the brain where the density of the neuron is the highest in the user's whole body, we will observe today we are only able to create one sensation in the hand. So hopefully both of these approaches of peripheral and source stimulation will advance. But this fundamental trade-off attributed to our anatomy should be kept in mind, and there's more room to explore. I would like to thank my collaborators, again, my colleague, Jacob Serfaty, and my advisor, Pedro Lopes, and these great people from Human-Computer Integration Lab at the University of Chicago. Thanks, and happy to answer your questions.
Thank you guys for the presentation. This is a great work, so that's
really amazing work, and I have two quick questions. How customized does it have to be for each user? Like, how much consistency is there across different users in terms of where you stimulate them and so on? That's one question. And then the second question is, can you say a little bit more about what it feels like?
Okay.
Is it pleasurable or is it pain?
Great. So first, I answer your first question, which is how custom or calibrated for each user. I would say we don't need much calibration indeed. So what we did for this study is like we first found the point that can twitch the hand, and we also find a point that can twitch the feet, twitch the leg. And then we defined these 2 points as a reference point and defined the range that these 2 points are on. And then we automatically define these 9 points. So even if we can create 16 points, we only have to calibrate for 2 to 4 points. And this is, I think, compared to EMS, this is much less of the work. And for your second question, sorry. So how does it feel like? We indeed did a study on that, and which I didn't talk in this talk, but majority of the sensation feels like tapping or vibrating, like 70% of the time. And the smaller portion is more like a pressure or skin stretching. This is a tactile part. And then the movement, like force feedback, is simply a twitching of your body, which is like EMS without skin tingling. And people really said like it is like stomping on a rubber ball or kind of like a recoil. And because we don't have any devices on the user's body, they actually see their hand, like nothing on their hand. So in terms of virtual reality interaction, it feels really natural because they just see their hand, like using my natural hand as mentioned by one of the participants.
We have another question.
Thank you for this very innovative talk. I'm Karin from Meta, and I had more or less the same questions, but I would like to, do you know how much design space you would have to make this more pleasant or even different? Like, is this the only sensation you can give, or you think that by tweaking some of the parameters you can do other sensation too?
Yeah, thanks so much. That's a really great question. So we actually fixed the frequency and pulse width of the stimulation parameters, and indeed we have a design space to create more different types of sensations. And I also want to add one thing to it, which is haptic source-effector can be achieved by transcranial-magnetic-stimulation, but it can be also achieved by other type of brain stimulation technique, like invasive or TDCS. We can talk more.
Last question over there, very quick, please.
Thank you for the talk. I have previous research on TMS use for stroke rehabilitation, and I wanted to ask how heavy was the headset on users' heads, and did any participants state discomfort or anything like that? Yeah.
Right, thanks so much. So the coil itself was 2 kilograms, and then the structure was 1 kilograms. And we are already iterating this device from this point. And by just simply switching the material from the metal to carbon fibers, we already succeeded in reducing the weight by 20%. And we can also search for decoupling the motors from the headset itself, which can also offset the device. In total, we can easily see like 50% reduction of the weight for the structure part. We can also customize the coil, so the coil can be also more lightweight.
All right, then please another round of applause for Yudai. Thank you a lot for your presentation. And now we close